Hello students, so continuing our lectures on solid-state physics. In the case of scattering, if e to the power I k dot r is incident radiation and e to the power minus I k dash dot r is the outgoing radiation, so the amplitude can be expressed in this fashion: the scattering amplitude, where nr is the distribution of the scattered and k is the scattering vector, which is the difference between k and k dash. As we have seen, it is equal to k out minus k in, and this is the scattering amplitude. And if Lg is the scattering amplitude, then we can write the scattering factor as equal to integration of Fj into this expression. E to the power I q dot r divided to the power I q dot g. In most cases, in experiments, the measured intensity is the square of the scattering amplitude, and to find out the scattering factor takes the form in this fashion. In the case of a BCC, x plus y plus z, and this term is reduced to the Fourier transform of f. And again, we can have the scattering amplitude is equal to fq, and it is equal to 2 delta q dot j if the q1 and q3 and q3 with the addition of these three is equal to even. So this is one of the conditions, that all the h-scale values should add up to give you an basis structure. And for place perpendicular to x, n lambda 2a sin theta is the diffraction condition. So if k is equal to 2 pi by lambda, we replace this lambda by 2 pi by k, and we ultimately get n into 2 pi by a into 2 sin theta dot k is equal to q1. So q1 is this quantity, and similarly, if this stands when the Miller indices is 1 0 0 1 0 0, and for 0 1 0 Miller indices we get the following values of q2, where it is cos theta and it is y instead of an x. In the case to explain semiconductors, we sometimes use single electron approach, mainly helpful in the case of alkali metals like lithium, sodium, potassium. And if we consider a box of sides L and L, and this is the Hamiltonian, so we get the following solutions: e to the power I k dot r for the wave function, and h cross k cross r by 2m is the energy, and k is of course 2 pi by L n1 n2 and n3. Now the since electrons are fermions, so each electron will have to have different quantum numbers. So if 2 pi by L is the main difference between the two electrons in k space. So for one electron uses up 2 pi L into d, where d is the dimension of the space. Let's take this amount of volume of the whole k space. For electron density in the ground state, it should be n divided by n to the power d. Now for a wave vectors less than the Fermi surface, we can have electron density 2 into VKF L by 2 by d by LD, and this is due to the spin degeneracy. This factor 2 comes. Now for the case of an electron density in 3D, we have 4/3 pi kF cube. So if we place in this, we get electron density as this value. And similarly, for the case of this is for d is equal to 3, it's with this value. Similarly, for the case of 2 dimension and 3 dimension, it is the area pi kF square, it is the length 2 kF. So these are the following electron density. Now the maximum energy is of course h cross square k square by 2me. This is the Fermi energy, it is the highest occupied energy level, and below the energy all are occupied. And electron density as a function of Fermi energy we can be expressed in this fashion, and which comes out to be actually equal to the density of states is equal to d by d of any. For the three dimensions 2D, 3D and 1D, we get the different density of states. This is for the 2D, m root 2 pi by h cross square 2 pi square. This is for 2D and this is for 1D. If we plot with respect to E, so this is the three types of density of states that we obtain.